Welcome to podcast number 2. This podcast is going to review the periodic table, ions, and then writing and naming formula, which is always a fan favorite. So we start off with the periodic table. It's a systematic catalog of the elements, so there is a method to the madness. They're not just all thrown on there. The biggest thing is they're arranged in order of atomic number. So if you look at the elements, the number at the top, which is the atomic number, goes up for each box. Now it does coincide with mass for the most part. The masses also go up, but there are some areas where the mass stays the same or the mass does drop just a little, and we know that's because of the weighted averages that are on there. So that doesn't allow it to be arranged perfectly by mass. All right, periodicity is kind of like the patterns that we can see. So if you look, if you look at the image, you can sort of see a pattern that by column, because HE would be on top of NE and then AR below that. So you can see as you're going down the columns or the groups, there are some common properties among those groups. And that has to do with the number of valence electrons giving the elements within the same group a similar amount of, having the same amount of valence giving them a similar properties, okay? So we know the rows are called periods, the columns are groups, sometimes referred to as families, and then elements in the same group have similar chemical properties, again, because they have that similar number of valence electrons, so that's gonna affect how they react. Okay, these are our groups that tend to be known by the names. The ones you want to definitely know are the alkali metals in group 1, alkaline earth in group 2, halogens in group 7, and then, or 17 is how we typically refer to it, not using the A names, and then the noble gases group 18. You don't really need to worry too much about the chalcogens. All right, nonmetals are on the right side, so we know we have that zigzag or that staircase that separates the two sides. Nonmetals are on the right side, with the exception of hydrogen over on the left. The metals are all these elements to the left and the two rows down here, because remember those would be right in here. The metalloids are the ones that run along that staircase. Does not include aluminum or polonium, Alpo, like the dog food. You can see right now that in this slide they're highlighted in that purplish color to show that they're a metal. All right, formulas. The small numbers close to the ground, like the subway, are the subscripts, and those are going to be to the right of the symbol. They tell you how many of that element are in the compound. So for example, if we're looking at CO2, the subscript 2 tells us that there are 2 oxygen atoms in every molecule of carbon dioxide. Okay, molecular compounds are composed of molecules and almost always contain only nonmetals. So molecular tends to be used as covalent. So if it's molecular, it tends to be all nonmetals, so like a covalent bond with 2 nonmetals. And then our ionics have the metal, but we're coming up to that a little later. All right, our diatomics. So these are called diatomic because they naturally occur as 2 atoms, di for 2, atomic for atom. So the ones that exist with the subscript 2 are H2, N2, O2, F2, Cl2, Br2, and I2. Something cool is that there are 7 of them, and they do form a 7 over here, but then plus hydrogen, always causing trouble all by itself there. I also learned a little mnemonic device called Brinkelhoff, and that just helps you remember the 7 elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So either way, however you want to remember them, but that is going to be important for you to know, because when we're trying to write and balance formulas, you're going to need to know if something has a subscript 2. So these ones, when they're by themselves, always have that 2. All right, there are some different types of formulas, and we are going to learn how to calculate them a little later. So for right now, this is just your definitions. So empirical formula gives the lowest whole number ratio of atoms. So it's basically the reduced formula. The molecular formula gives the exact amount of atoms in the compound. So if there's 7 hydrogens, it'll say H7. Okay, whereas empirical is giving you that reduced form. If they all have a common number that they can be divided by, the empirical formula will be that lowest possible ratio. Okay, then the next two are on this slide. So structural formula, those show the order in which the atoms are bonded. So if you were to try and write out a big diagram of the elements, the structural formula would give you the order in which they occur. Okay, and the last one on here is perspective drawings, and this would be like this here. See, that's labeled. A perspective drawing actually shows you the three-dimensional angles and the way that it is arranged. So the little line like this would actually mean that it's going into the board. So if we're thinking like 3D, it would be going in, and then this like fatter triangle is indicating that it's actually coming out of the board. So you kind of have to use your visualization to try and sort of picture how that might look. These are some other ways that you may see models drawn. All right, ions. So an ion is when an atom has lost or gained an electron, so now it has a charge. A cation is positive, and those are our metals, so our elements on the left side here, and then aluminum. Remember that cations are positively charged, okay? And then our anions are negative, and those are typically going to be our nonmetals over here, as you can see. We can have other cations and anions, so like some of these transition metals can form cations, okay? So anything that forms a positive charge is technically a cation. Same over here with our anions. Okay, here are some common cations, just so you can see some of them. These are some that we'll be dealing with through the year. So it's just a list of a whole bunch of common cations. This one here is a polyatomic ion. We're going to be talking more about those in a little bit. And then a few common anions have negative charge. We have a few more of our polyatomic ions involved in this list. Polyatomic just meaning it's made up of more than one different atom, so different elements with a charge. All right, ionic bonds. So an ionic bond is when you have a metal with a nonmetal. So the example here is NaCl. So the Na forms a cation, and then the Cl forms an anion. So basically what's happening is the metal is giving away its electron. So remember, electrons are negative. So when you lose an electron, you become more positive. And then the chlorine is accepting that electron or gaining that electron. So because it's gaining a negative, it's becoming more negative. When we write formulas for our ionic compounds, we use the crisscross method. So hopefully this is a review for you. You look up the charge of each of the elements, and the charges do go by their group number. So remember, group 1 is +1, group 2 is +2, group 3 is +3. Shouldn't really see any in group 4, but we'll say +4. Group 5 is -3, so then they start going down and negative. Group 6, -2, group 7, -1, and then group 8 are our unreactive noble gases, so they won't form ions. These are all listed in the table on your sheet here as well. So you find the charge of the cation, find the charge of the anion, and then you just crisscross them, move them to the bottom, and lose the positive and negatives. So the 2 from the Mg2 plus goes down here, as you can see here, and the 3 from the N3 minus goes down here, like you can see right here. Okay. If they are not in the lowest whole number ratio, we do reduce them for ionic compounds, so you would cancel them out when possible. And as mentioned, this is often referred to as the crisscross method that we use for ionic formulas. All right, now if we need to be able to write an ionic formula, we need to be able to name it. So naming ionics is really easy. You write the name of the cation, which is their first element, and then you write the name of the second element, or the anion, but you change the ending to IDE. So if it were NaCl, it would be sodium, and then instead of chlorine, it would be chloride. If the anion is polyatomic, then you just write the name of that polyatomic. You don't change anything on those. Okay, if the cation can have more than one possible charge, like our transition metals, some of them can be +1 and +2, or they can be +2 or +3. So in those cases, we want to write the charge in the center with a Roman numeral so that we know which particular ion we're referring to. All right, so you will need to know the names of the polyatomics, most of them, but there are some little tricks to try to kind of help you to remember them. So some patterns in oxyanion nomenclature, oxyanion being involving oxygen, okay, and having a negative charge. So the one with fewer oxygens tends to end in ITE. So if we're comparing those with these, nitrite has 2 oxygens, so it's got the ITE. The one with more tends to end in ATE. So the one that has more oxygens has that ATE. The one with less has the ITE. So that can kind of help you try to remember some of the names of the polyatomic ions. Oops, sorry for the pop-up. Okay. So here's another example. We have chlorite, and then more oxygens would be 8. Okay, so this little flow chart kind of thing down here can sort of help you visualize that. Okay, and then sometimes we see hypo at the beginning. So the one with fewer oxygens has the prefix hypo, and then sometimes if it has more, it would have per in the front. So just some little patterns that we see. Okay, so this is some practice for you with writing the names of these ionic compounds. You will need to refer to your polyatomic chart if you don't know the names of them. So I would recommend you pause right now and try and figure out these names. Okay, so hit pause and do it. Now you can check your work. So here are the answers. So hopefully you got them right. If there's one that you didn't understand or you don't know why it is what it is, please make a mark next to it so we can go over it in class. Okay, you may need to pause again because I'm going to keep moving the podcast. All right, same thing here, except now we want to write the formula. So go ahead and pause and write your formula. Again, you can check your work. Okay, so here are the correct answers. Again, if you didn't understand something, please make a note of it and we will go over it in class. All right, binary compounds, often referred to as covalent. They're going to list their less electronegative atom first, so the one that has less attraction for electrons tends to be first. And then we use our prefixes. They should look kind of familiar based on geometry and some of your math classes. So you're going to want to know these prefixes. One thing to note is that mono is not used when it's the first element. So if it's like CO, carbon monoxide, we don't say mono carbon monoxide. I don't know why, but that's just how it is. So mono will never be used on the first element. Okay, for covalent, just like with ionic, you're going to change the ending to IDE. Okay, so here's some examples you can fill in on your sheet in the boxes. Okay. And then we do tend to drop that middle extra vowel. So like N2O5, we would make dinitrogen pentoxide. If you left the A, no one's going to mark you wrong, pentoxide, but technically we would drop that A. Okay. So again, pause your video, try these out. So it's a little bit of writing the name and a little bit of writing the formula. Check your work. Hopefully you got them right. If you have questions, bring them into class. We do not reduce for covalent, only for ionic. All right, and lastly, we have acid nomenclature. So if it ends in IDE, you just change it to ic. So hydrochloric acid, hydrobromic acid, hydroiodic acid. If it ends in ATE, change it to ic. I'm sorry, the other ones you add the hydro to, but these you don't.